So we know that rand_n generates Gaussian noise. Let's see how it actually works. If you call rand_n without any parameters, then it returns a random number. Here we get 0.76388. Run it again. A different number, 1.3958. You can pass in dimensions to rand_n to generate a vector or matrix filled with random numbers. Let's say we want a row vector of 5 columns. So 1 row, 5 columns. Each time we run this, we get different sets of numbers. As you might have guessed, we can generate a two-dimensional matrix of random numbers as well. Say we want 2 rows and 3 columns. Since these are a bunch of random numbers, we call this noise. What is interesting is that rand_n draws these numbers from a Gaussian or random normal distribution, hence the n in rand_n. A Gaussian distribution has a probability distribution function that looks like this. The center or mean for rand_n is 0 and the standard deviation is 1. The standard deviation is a measure of how spread out the distribution is. I mentioned this is a probability distribution, which means getting back numbers that are close to 0 is highly likely, whereas numbers far away from 0 are less likely. How do we know for sure that rand_n is actually sampling from a Gaussian distribution? Well, if we had enough samples and distributed them among bins, and we counted how many numbers landed in each bin, then we would see a pattern similar to the probability distribution function. Let's try that. How about we start with a vector of 100 numbers? Instead of displaying the numbers directly, let's compute a histogram. Hist accepts a vector or matrix of numbers as the first argument, and as an optional second argument, you can pass in bin centers. Let's say we want the centers to be integers from -3 to +3. Hist returns two values. One is the count of elements, which we want, and the second is the bin centers. Let us display the bin centers and the counts in a tabular form. We'll create a small temporary matrix, with the first row being the bin centers and the second row being the counts. As expected, the center has a high count and the ends have low, in fact 0 counts. You see the same behavior no matter how many times you run it. For a visual representation of what's going on, how about we plot these numbers? X-axis will contain our bin centers and the counts will be on the y-axis. We see something that vaguely resembles the Gaussian probability distribution. To get a better picture, we need more bins. You can generate a sequence of uniformly spaced numbers using the linspace function. Here we can replace this vector by writing -3 to +3, 7 different numbers, that is, including 0. Let's make sure this is the same as before. Note here that the bin centers are same, as expected. Now we can easily increase the number of bins. Say we want 21 of them. I'm going for odd numbers because I want to include the 0 in the middle. Displaying so many numbers wouldn't be useful, so let's comment that out and see what the plot looks like. Clearly, we have better resolution along the x-axis, but what's going on with these spikes? I think we need more data. Let's bump up the vector to 1,000 numbers. Now you see the familiar bell curve slowly emerging. Let's increase the number of samples further. There you go. In addition to rand_n, you can find other random number generation functions in Octave or MATLAB, such as just rand. This samples numbers from a uniform distribution. rand_i generates random integers. Feel free to play with these functions.